Morning, everyone. So, in the last couple of lectures, we have seen different types of time series models, which starting from white noise, random walk, AR, MA, ARMA, ARIMA, seasonal ARIMA, etc. And we have seen some of the properties in terms of its expectation, variance, autocorrelation function, autocovariance function, how the behavior of the autocorrelation function, etc. And in today's lecture, now we have three more topics in this univariate time series. Uh, One is on forecasting, another one is on estimation of the parameters, and the third one is residual analysis, or I would say identification of the appropriate model, or uh, you know basically you can say that residual analysis, verification of the appropriate model or verification of the assumptions. So in today's, so that will be the third one. So in today's lecture, we are going to discuss forecasting. So when I say forecasting, I there are two things. Initially, we start with the forecasting of a stationary series. I'm not going to assume a particular model. Then later, of course, that's just for the introduction of the topic. And then later, I will assume a specific linear structure to that, and then try to see that how this is going to help in terms of identifying the forecast or in terms of getting the forecast. Now, in this whole discussion, we sort of assume that uh, the parameters of the model are known, which is not true in a real sense. But what we are trying to find a kind of an optimal forecast now, and then these parameters which are appearing in the optimal forecast will be replaced with appropriate estimators. So that requires a estimation theory of time series models that will be discussed in the next lecture. So we start with the question, what is the difference between forecasting and predicting? Well, most of the textbooks use the same thing, same terminology. I may also use the same terminology, but there is a slight difference when we say prediction and when we say forecasting. Forecasting basically uses the previous information to forecast or to say something about the future or future values, whereas prediction could be we may use, we may not use. So many a time the prediction need not use that. Well, we can call the forecasting also as prediction. So in that case, both are same, but otherwise it is not. So this is what given data or information at time t, say fn. So this is my data at time point n. And then I want to say something about n plus l for some l greater than 0. Now we have seen in your regression analysis, when we try to come up with a forecast or when you try to come up with a regression function, uh, there is some kind of an optimality in our mind. What does that optimality means? So it should minimize whatever that the error in that whatever that we are proposing. So for example, if the actual value is xn plus l and the forecast value is xn plus l hat, then the expected value of xn plus l minus xn plus l hat whole square, that should be minimum. So you should find your xn plus l hat in such a way that this is minimum. What is that value? Well, then there can be several questions. Why expected value square, that is mean square error in the prediction, or forecast mean square error? Well, these questions can be answered. You can, instead of square, we can go for absolute, we can go for any kind of loss function. These are all subsequent developments. So initially we start or we restrict to squared error. So there are two things here. One is the best forecast or the best linear forecast. So the best in terms of minimizing the mean square error. And that is given by expected value of xn plus l given fn. The one which minimizes this. This is known because this I don't have to prove this. Well, you can prove also uh, by writing down the expression for, say for example, you can actually write down expected value of, sorry, xn plus l minus xn plus l square, which is xn plus L. So I'm trying to say that, okay, this is the one which minimizes that. So if that is minimizes, if you have anything else other than this, then this error square should be larger. I mean, that's what, sorry, I think I need to. Yes. So we are saying that in terms of minimizing this. Okay, let's go back and then try to see that. Now, this is the best forecast, but best forecast, we may not be interested in the best forecast because the best forecast, if you want to compute, let me go back, because if I want to compute the best forecast, I need to obtain the distribution, I mean the expected value of this x1, x2, xn, say, because my fn is this. And this will force me to have, say, xn plus L and f of xn plus L given xn dxn plus L. So I need to actually obtain something like this because this is the expectation. So we need to compute this conditional distribution of, or the conditional expectation of this. What does it mean? It means that if you rewrite this, you need to actually get this. That means we need to find the joint distribution of this whole thing. Now, this is not like a regression setup or a usual IID inference because these are dependent. So when you write the joint distribution, it's not very easy to do that. So most of the time, and that is of course in the case of arbitrary distributions also, like when I say arbitrary distribution, if it is a normal, it is easy to write multivariate normal and even subvectors of multivariate normal. But if it is an arbitrary distribution, this computation is highly involved, so it may not be possible. So in most of the time, and not only that, when you have a multivariate normal, you have a result, like for example, if x1 given x2 is multivariate normal, suppose this x1, x2, you're partitioning it like this. So I have this x1, x2. This is a vector. Of course, you can actually consider it transpose. So x1 given x2 is mu1 plus sigma 1, sigma 1 2, sigma 2 2 inverse, sigma 2 1 into x2 minus mu 2. This is the mean. So this is something like, if you now consider, it's like, if you are in the univariate kind of setup, I should not say equal. This is of the type, so this is of the type a plus bx. If you are considering y as x1 and this as x, so this is of the type a, because you get this and this will be combined and this will be multiplied by this. So in a scalar setup, this is something like a plus bx format. In a vector setup, of course, this is a vector and this is a matrix and this is a vector. So this is, the entire thing is a vector. This entire thing is a vector. So what I'm trying to say, that the advantage of normality is that this best predictor will become linear. That's the beauty of it. So that's why sometimes, even if whether it is normal or not, we go for linear predictor and then verify the normality later, right? So that's what we do. So sometimes best linear forecast is of interest. Now when I say best linear forecast is xn plus L, the forecast is equal to a naught plus a1 xn plus a2 xn minus 1 plus an x1. You may wonder, why didn't I write a1 x1 plus a2 x2 etc. an xn? Well, you could have written, because anyway a1 a2 an are not specified, but there are some advantage of writing like this which you are going to see little later. Uh, So when they are now the question is that when these two are same. So these two are same when you have a multivariate normal distribution of x1, x2, xn, xn plus L. And in most of the times it is literature. When I say forecast, I'm not going to forecast a long-term forecast. I mean, because we do a short-term forecast, like few months or a few weeks ahead, few days ahead, because there is a dynamical force or dynamical system that actually can change the whole model. And so the forecast need not be. And these are basically, when I say linear, it's a kind of a linear function. I mean, linear in the sense that it's of this type. And we continue to assume that this structure continue to hold even at n plus L. So if L is far away, that assumption may not be very true. So by the way, this L is called as lead time. So let xt. So I'm not assuming any particular structure for the xt, but we simply say that xt is a stationary series with expectation mu. And suppose we have observed x1, x2, xn, we wish to find the best linear predictor or the best linear forecast function xn plus L, where L is called the lead time or forecast horizon. So we will denote this quantity by Pn hat Pn curl xn plus L. So this is just a notation. Pn curl xn plus L is essentially means that this quantity. What is that quantity? Pn curl xn plus L is this quantity. Expected value of xn plus L given x1, x2, xn. So now that we don't consider that actually, rather we consider this. So we say that this is equal to this. You may want ask the question why, how, if it is not equal. So that is where we try to test the normality of the data. So if it is normal, then it will be equal to this because the predictor, the best predictor, will be a linear function. So the best predictor is a linear function of the given observations, and these coefficients are obtained in such a way that this error square, that means the forecast mean square error, this is mean square means expected value of this, is minimum. So you are trying to minimize this and obtain a naught, a1, a2, etc., an such a way that this is minimum. How will you do that? Well, that's not difficult because you can differentiate this quantity with respect to each of these coefficient. That gives you kind of n plus 1 equations, equate them to 0, solve for a naught, a1, a2, etc., an. So you'll get the answer. So differentiating FMSE with respect to each AJ and solving, we get this equation. So actually there are, I'm just splitting them into n and 1 because you may be able to write a naught very easily because a naught doesn't have these xi's. So when you differentiate that, it simply vanish all of them. So it is very easy to get the a naught. So a naught is just mu into 1 minus summation 1 to n aj, and this is not difficult. You actually differentiate this with respect to n naught means it's 2 into this quantity with a minus sign, and then you are equating to 0, minus doesn't matter. So expectation of this quantity is like because this is mu, so you have mu and each of them is mu. So it's the a naught if you take on the other side. Here there is no excess here, so this can go other side. So mu into 1 minus summation 1 to n aj. That's a naught. But you can't get this equation is not enough because this involves the unknown quantities aj's over here. So basically what we require is we also may require I mean like sorry, the subsequent A2, A1, A2, etc. n. So that can be obtained by this equation, gamma n into an is equal to gamma nl. What are these gamma n? Where from it is coming? Because you are differentiating each time with respect to ai's. So if you are differentiating with respect to x1, sorry, a1, then there will be an xn here. So you have to multiply this entire step twice into this quantity into xn. So it is like expected value of xn plus L into xn that gives uh, this particular covariance. Similarly, each of them, you see. So these coefficients, this actually turned out to be gamma n is nothing but gamma naught, gamma 1, etc. This matrix, that is nothing but the autocovariance matrix, and this a coefficient is nothing but a1, a2, an, and the right hand side gamma nl, this is actually vector because you are multiplying a matrix with this vector, so this has to be vector. So don't confuse this between the gamma l. Gamma nl means there are n components to that. Gamma l is one of the components. So this gamma nl is gamma l plus 1, etc., gamma l plus n minus 1. So if this is, this is, so basically how do you get, how do you get this best predictor? Best predictor is obtained once you compute these AIs. And AIs can be computed when you have just invert this matrix and put it over here. So you multiply by the inverse of this matrix on both sides, so you get the AN here. And once you have the AN, you can get the A naught. And once you have the A naught and A1, etc., all the AN means the AN vector. Once you have this, you get the best predictor or the best linear predictor, right? And so what is that required to get this? What you require is this quantity and this quantity, because this is to be found, the inverse of that has to be multiplied with this to get an, and of course if this mu equal to 0, this term doesn't arise, this will simply vanish. So you're directly dealing with this, uh, right? So this, the best predictor is given by this quantity, or you may write it as mu plus summation aj xn plus 1 minus mu, where this is not difficult because this is actually a naught. I have mixed it with this. You see, a naught is this, so I mix it with that. So it is mu plus summation 1 to n ajxn plus 1 minus j minus mu, where a's are the solutions of this equation, right? So this is how you find the best linear predictor in the case of a general stationary process. Now let's look at the forecast mean square error corresponding to this. So what is the forecast mean square error in this case? So the forecast mean square error is this quantity square of this, and square of this means that you have basically I'll be writing xn plus 1. This when you write, because we already seen that what is that, it is mu plus this quantity. So when you subtract that, that mu subtracted here, and the other quantity is over here, so you are just subtracting this and then take the square. So if you take the square, now you can, it's like a minus b square, this square of this minus twice into this quantity and plus the square of this. So this can be further simplified because there is an expectation those quantities can be simplified in terms of the covariance function. So this simplifies to gamma naught minus twice summation aj and the covariance between this and this. And what is that? It is gamma of L plus j minus 1, right? It's like this subscript minus this subscript. So this subscript minus this subscript means n goes. So what is remaining is L plus j minus 1. So that is what the cross product term. And then the final term is the square of this and the expectation. Now the square of that and expectation, what will happen is that we will be able to write in this manner. There will be I equal to j, j equal to k terms here, but what happens that when j equal to k, that will be simply become the variance term. And then of course you will have aj square over there. So you could have written like aj square and this square of this variance plus, then there are covariances, because it is like summation xi. When you compute the variance, it is summation xi square plus summation xi xj and the covariance between them. So exactly you will get this. Now if you rewrite this, you can see that this is gamma 0 minus twice n prime gamma nl. Gamma nl is a vector. You might have seen it in the previous slide. This is my gamma nl. And this is quadratic form. So you know some xi ax, x prime ax is summation aij xi xj. Exactly same thing here. X prime ax is summation aij. This is ajk Aj, ak. So this can be written in this manner. Now what happens that if you look at this carefully, gamma n an is gamma nl. So you can see that this is to minus 2 an prime gamma nl, an prime gamma nl. So one of them get cancelled. So gamma 0 minus an prime gamma nl. And an is equal to this inverse into gamma nl. So an prime is gamma nl prime, this variance covariance matrix inverse of that. So if you substitute that, so you get gamma 0 minus gamma nl prime, gamma n inverse gamma nl. Okay, so this can be worked out very easily. So that leads to this formula. So what is this all about? This is the forecast mean square error. And this is corresponding to the best linear forecast. And what is the best linear forecast? Best linear forecast is given by this quantity. And in that, what are AI? AIs are obtained by this formula. And what is A naught? A naught is like this. So this is what your, or you can write like this. The best linear forecast is given by this equation. Actually, we can simply ignore the A naught because that will come in terms of the mu. So if this is what we consider the best linear forecast, okay, where ages are obtained by this equation. So what is required to find the best linear forecast of a stationary sequence? Covariances, right? So you need two types of covariances. One is this covariance matrix, which is basically the covariance of the given data. Because you say that you have n observations, so you can say gamma 0, gamma 1, gamma 2, etc., gamma n minus 1. So this is a matrix corresponding to that. And then there is another vector that you have to find, and that vector is basically obtained as a covariance between what is the lead time that you are looking for. So n plus l. So you will be starting from there, what all the points there. So you will have gamma L plus 1, etc., gamma L plus n minus 1. So these terms are going to come in this vector. Okay. So this is, so forecast mean square error is also in terms of the covariances. Now we can see that if you consider such kind of a best linear predictor, that will turn out to be unique. That's not difficult. Proof is simple mathematical proof. So what is the best linear predictor? The best linear predictor is given by this quantity. Sorry, this quantity. So now suppose assume that there are two best linear predictors. So what way these two can differ? It can differ by this coefficient, because we are saying that the best linear predictor is this. So if there is another one which is linear, this coefficient simply changes. So you'll have another set of coefficients. So we have two sets of coefficients. Assume that there are two sets of coefficients. So if possible, there are two distinct solutions, AJ1 and AJ2. And then what you need to do is that take the difference between them. So if you take the difference between them, uh, you can see that the difference turns out to be this. A01 minus A02 plus AJ1 minus AJ2 xn plus 1 minus j. Now what you do is that if you start computing, you remember you had the normal equations here. Where is the normal equations? I didn't write the normal equations explicitly here, but these steps involves n plus 1 normal equations. Because you are differentiating this with respect to A0, with respect to A1, etc. So when you differentiate this with respect to A1, you are now saying that expected value of that quantity is equal to 0. And that leads to this. So what you will have is this D quantity, if you consider, you can actually now show that this d square can be written as d into this d. One of them I write in this format, other d I keep it as such. Now if you look at the normal equation, now you can see that using the normal equations, it is possible to show that the expected value of d equal to 0 and expected value of d square equal to 0. So if you have a random variable with expectation 0 and second moment 0, then that random variable is 0 almost surely, because second moment is variance. If variance is 0, that means there is no variation at all, and the expectation is 0, so the random variable almost surely it is 0. So d is 0, it means that d is the difference between them. So what we are saying that if there are two best linear predictors, then they are almost surely the same. Now almost surely is important because we are talking about random variables. Okay, that's why this almost surely comes. So this proof, so what is required here, you to do is, I have given the hint, this quantity you need to verify. How will you get this quantity can be verified? D is already here, so you can take the expectation of this. So you can actually write this and then use the fact, the linear equations, or you can directly go to the linear equations and show that the expectation of the first term when you differentiate with respect to a naught is equal to 0, and another expectation with respect to differentiate with respect to this, that is also 0, so their difference is also 0. So you will get this quantity is 0. Similarly, square, now I am not telling that, you have to simplify this and then show that. So where do you get that? You go to the second set of uh, the second equation corresponding to the second normal equation corresponding to the minimization. So that can give you that this d square equal to 0. So this shows that d equal to 0 almost surely. Now let's look at, so this I've given you the best linear forecast without specifying to a particular model as such. Let's look at what is happening in the different cases. So for example, if you have AR1 xt minus this vxt minus 1, in this case, so let's look at AR1. So AR1 is basically xt is equal to phi xt minus 1 plus zt, and I have x1 x2 xn. This is the observation, and then I want to say something about xn plus forecast. So I would say pn, uh, pn xn plus l. Okay, according to our notation, this is not here. So what is this? So this is given by expected value of, so this is what we need to compute. So what we do in these cases, we go for a recursive method. So I will write this xn plus 1 as phi of xn plus zn plus 1. And then I take the expectation of this. So this is given by phi of xn, sorry, expectation of xn given plus expectation of zn plus 1 given this. And this is 0 because this is n plus 1 and this is up to n. And since xn is given, expectation of xn given this is phi xn. So what is the best predictor? So pn xn plus 1 is given by phi xn. Now if you continue this, suppose if you are getting pn xn plus 2, so what is this? So I need to compute. So your equation is xn plus 2 is equal to phi of xn plus 1 plus zn plus 2. And if you do the same thing over here, we can see that pn xn plus 2 is equal to phi of expected value of xn plus 1 given x1 x2 xn plus zn plus 2 given xn. And what is this going to be? Phi of, and this we have already obtained, which is here in the previous, here this we already obtained there. So if I rewrite the answer there, so that answer is phi xn, and plus this is 0 because this is n plus 2 and this is up to n. So this answer is given by phi square xn. So what is actually happening is that this is, don't think that this is like so easy in all the cases. This changes actually depending on what type of process that you are considering. So in the case of, so this is phi square xn, which I have now obtained. So in the case of AR1, the two-step predictor. So, but the two-step predictor requires the one-step predictor. So that's how we got phi square xn, etc. It goes like that. Now, in the case of AR2, what will happen in the case of AR2 if you have in a similar way, because you will be writing phi xt minus 1 plus phi xt minus 2, so I'll be writing xn plus 1 here, so then this is xn and this is xn minus 1 and this is xn plus 1, and then you take the expectation of that given the data, so that given the data this reduces to, you have xn here, so you have, that will continue like that, and you have n minus 1, so you will get this. So, and this is 0 because this is n plus 1, so this will be like this. So now what is p xn plus 2 is xn plus 2, you write xn plus 2 here. So in the case of AR2, phi 1 xt minus 1 plus phi 2 xt minus 2 plus zt. So what I will do is that xn plus 2 is equal to phi 1 xn plus 1 plus phi 2 xn plus zn plus 2, and then we need to compute pn. See, this n stand for what, up to what time the data that's what basically n stands for. So this is given by the expected value of phi 1 xn plus 1 given xn plus, so this leads to phi 1, and now you have expected value of xn plus 1 given xn. So xn plus 1 given x1 is to xn, so which we have already computed in the case of, so I would like to show you that, and that is here phi 1 xn plus phi 2 xn minus 1. So I will write that, and plus phi 2 xn is given, so this is phi 2 xn, and plus this is 0. So what is that? You get the answer in this case. It's phi 1 square xn, phi 1 phi 2, so xn minus 1 plus phi 2, this is not x2, this is actually xn, because sorry, so this is, oh, so you will be able to, I mean, like phi 1 square plus phi 2 xn plus, so you see phi 1 square, this xn is here, so phi 1 square plus phi 2 xn plus phi 1 phi 2 xn minus 1, that's what I have. So phi 1 square plus phi 2 xn plus phi 1 phi 2 xn minus 1. Now I told you, how do you know these things, because this has to be, I have assumed that your x1, I mean phi 1 phi 2 are known, so phi i's are assumed to be known at present. So let's go back. Now, this recursive, so this is called recursive forecasting, because you develop, even if the lead time is L, you cannot directly go to N plus L. So you have to get N plus 1, you have to get N plus 2, N plus 3, and then you have to get N plus L. So the linearity helps you subsequently because the expectation actually goes through in the linear structure very easily. Now you see, I did not. You may wonder that, oh, but you said so much of stories. I mean, like I have to actually get this A1, A2, and then you found. I mean, where is those A1, A2 here? Well, that's where I have the advantage of linear structure. So that's why we are basically going for this linear kind of structure, AR, MA, etc. Because if you don't have that kind of a structure, I have to actually solve this equation gamma n an is equal to this gamma n l. Uh, so I need to get this an's the vector by inverting this here and then putting this here. And then once you have the an vector, I have to actually also obtain the a naught. So it's like the best predictor is given by a1 xn plus a2 xn minus 1 plus etc. plus an x1. So this is the best predictor. How do you get this a naught, a1, etc.? By inverting this equation as well as that a naught you obtain by the first formula. A naught is here, this one. This is a naught formula, right? Well, if you have mu equal to 0, this is a naught is 0, so it doesn't contribute, whereas this contribute. So that's where. So for all illustration purpose, we take mu equal to 0. Now let's look at a different model, MA1 model. So if you have MA1, how does it look like? So in the case of MA1, this it's Pn. So what is MA1? MA1 is given by this equation, xt is equal to zt plus theta zt minus 1. So if I want to get n plus 1 or n plus L, what I need is to compute expected value of x n plus 1 given x1 x2 xn. So it is like expected value of zn plus 1 plus theta zn given x1 x2 xn. So this is nothing but expected value of zn plus 1 given x1 x2 xn plus theta times expected value of zn given x1 x2 xn, and this is 0, this quantity, because this is n plus 1. This is not 0, this is actually depending on that. So you may have to actually find theta times expected value of zn. Now zn can be obtained, so what is that expected value of so Zn, if you rewrite this, Zn can be written in terms of uh, excise. So what I have is Zn is equal to, so you can look at this, that's what I'm trying to do. So what happens that this is basically expected value of Zn given x1 x2 xn, so theta times of that, and that is what this is. So this is Zn given x1 x2 xn. Now this is not 0, because this is 0 only if this index is this subscript is larger than this n. Whenever it is smaller, it is not 0. So this needs to be obtained. So how will you obtain? And that is very easy, because you can use, that is where your invertibility condition comes. So I will be able to write, if I able to write Zn as summation j equal to 0 to infinity of psi j, or some pi j xt minus j. So basically what I am doing is I am writing this as xt minus xt minus, so this is xn minus j, because you have written n here. So xn minus j. So I am writing in terms of xn. So what is this? This is nothing but xn into pi naught, which we generally take it as 1, plus pi 1 xn minus 1 plus etc. Say pi n, and this is suppose this is x1, pi 1 xn minus 1, pi 2 xn minus 2, and pi n uh, pi n minus 1 x1. Okay, pi n minus 1. So what you have is, then you may ask, but this is going up to infinity. Well, theoretically you can go up to infinity, because this is actually rest of the observations you can have. But when you have given a data, you don't have the observation beyond x1. I mean, unless you do a backcasting, you have to for backcast and then obtain. So most of the practical purposes, we consider this and then take this as the best predictor of uh, Zn. That means this is the, and then you have to multiply this whole stuff with theta. Why I wrote this? Because rest of the, you have actually x and x1, and then you have x naught, given all those things. You can actually compute. I mean, it's not over, because this will be, for example, this will be pi n x naught. This will be pi n plus 1. You will have x minus 1. X minus 1 is, it is a kind of, you don't have minus time point, but basically what we are taking is the time can run backwards, just whatever the time point you can run backwards. But what happened from an observational point of, that is from a process point of view. From an observational point of view, we are stopping at this point, and then we say that, okay, you will be able to write it in this manner, and you take this as your so now when you take right Zn in this manner and given x1 is to xn, all these constants, because x1 is to xn are constant, so you get this as a best predictor of Zn. And then the best predictor of xn plus 1 is theta times of this. So this is how you actually obtain this. So that's what I have written here. Actually, in the case of moving average, I did not use moving average idea over here. But because you can actually see that what happens to these pi j's in the case of moving average, because what I have written is a general one, but when you actually go for a moving average, this pi j's will turn out to be theta into minus theta to the power of j minus 1 xn minus j. So basically what you have is the best linear forecast. So always forecast has to be in terms of whatever you observe. You cannot write in terms of z or something else. So forecast has to be based on what you observe. So now what happens that you can see that in this case how these pi weights and psi weights are useful in forecasting, because these are nothing but the pi weights. Pi weights, what I mean is you have invertible process and you are inverting that, and then when you invert, this turns out to be pi weights. Well, this is going to change depending on what process that you're talking about. So, you see, if you're talking about an MA2, this will be a different weights over here, or these pi's are going to be different. And psi weight is nothing but you will be writing x in terms of past z values. So now, what is this corresponding in the case of ARMA? So in the case of ARMA, you can see that you have such a big equation, ARMA PQ. The advantage of all these thing is I'll be able to write the n plus 1 as this n plus 1 minus j. So summation of this given this, and when I come take the expectation where x1 is to xn are given, what happens that this will be Zn plus 1, because I'll be writing xn plus 1 here. So you can just write the xn plus 1 equation, take expectation of that with respect to given x1 is to xn. So you will get these things. So you see, you need to have all these predictors required. So this is a notation, that expectation notation is basically, we call it as prediction operator. So you can say Pn curl is the prediction operator, which is obtained by conditional expectation, given the data. So now what happened that I cannot call this as a predictor, because this involves zi's which are not observable. Xi's are okay up to n, but these are not. So we need to actually rewrite this whole thing in terms of xi's. So how will you rewrite this? And these quantities are given by this for j greater than 0, and these quantities given by Zn plus 1 for I greater than 0, and p equals Zn plus 1 equal to 0. which means that this equation actually reduces to something like this. But these are not observable. So we need to replace this with the corresponding xi's. Now, you can't simply just replace it with x. For that, we use the invertibility idea. So I will rewrite z in terms of invertible process, and then accordingly I'll get the corresponding coefficients over here. So now use the equation model and replace each of the zn plus I with the observation x1, x2, xn. That replacement is done based on the assumption of invertibility. So that is where you basically require the ideas of invertibility. So using the above procedure, it is possible to find best linear predictor of. In fact, we can also obtain the best linear predictor of a mixing observations, because so by this what I mean is, it's not necessary that we think that okay, we have x1, x2, xn, and then I am going to predict xn plus l, something about this. Actually, these methods, what does it depend on the best predictor? It depends on the covariances only. Covariances of what? Among this, which is gamma n, and with this to this, which is gamma nl vector. So you see, that's how you get, and your A is nothing but gamma n inverse, gamma nl. So once you have an, your predictor is ready. So which means that this need not be lying over here. Even if it is lying here, you will be in a position to find that by using this method. So for example, if I have x1, if I have x2, which is not available, and I have x3, I'll be able to predict the best linear predictor of x2 using x1 and x3. So this can be obtained. So it will be some function of, say, a naught plus a1 x1 plus a2 x3. Something like this. We need to obtain these quantities. And that quantity is going to depend on what? It's going to depend on the covariance between, so in that case, the data is x1, x3, and this fellow is x2 here. So you will have a gamma here, and you will have a corresponding gamma here. What is this gamma about? This is between 1 and 3, and 3 and 1, and the variance of 1, variance of 3. This is between 1 and 2, the covariance, and 1 and 3. So I'll have the corresponding vector. So I'm talking about this. This is the gamma NL vector, and this is the gamma N matrix. So N is 1 and 3 here. So don't think that when I say this method of prediction is useful even in obtain observation which are missing, because you can get the best linear predictor of that missing observations. So that's what this is all about. It is possible to forecast XM where if I have this data and XM is missing. So I have illustrated that in a simple AR model, because that forecast is depending on what? It's just depending on the covariance matrix. Of course, when I say covariance matrix, it can depend on the correlation matrix also, because you divide by gamma naught, covariance become correlation. So you can see that the best linear predictor of, if I have x1, x3, x4 available and x2 is not there, we can get the best predictor of x2 using this covariance or the correlation matrix. So how will you obtain that? So you will have this R3 and rho 3. By the way, this is not very difficult. This R3 and rho 3 is basically coming from here. Sorry. See, this is, you divide by gamma naught. So this will be R matrix. And divide by gamma naught, this will be rho matrix. Okay, so that's what it is. So that's where you get. Dividing on both sides is not going to change. So when the equation is in terms of covariance matrix or correlation matrix, it hardly matters. And so that's what I have written here. So A3 is R3 inverse rho 3 1. Now rho 3 1 is basically, this is the correlation between x2 and x1, which is of order 1, so 5, x2 and x3, which is of order 1, which is 5, x2 and x4. So in an AR1, the correlation between x2 and x4 is 5 square. So that's what this matrix. And here it is actually the variance covariance, the correlation matrix of this. So correlation between x1 and x1 is 1, x1 and x3 is phi square, x1 and x4 is phi cubed. So you see that, and this is just a transpose of that. So you have this particular matrix, and once you have this, the A can be obtained, this, and once you simplify that, you will get the A1, A2, A3. So the best linear predictor is given by A3 prime W. What is W here? this x1, x3, x4, the data. Okay, so the FMSE can be obtained using the formula which I have mentioned. This I am leaving you to verify. So the FMSE of in this case is given by this equation. So now the question here is, if n become larger, your gamma n is going to be very large. So if your n is large, so because you need to find A, which is gamma n inverse and gamma n L, and if n large, this computation will be difficult. So this is really difficult to find the inverse if n is large. Or in other words, so what is that you are doing? You are trying to find gamma n A is equal to gamma n L. So it's like you are solving a system of equation Ax equal to B. So if you have a method of doing this without actually getting the inverse of the matrix, then that will make the life easy. So there are certain algorithms which create some kind of a recursive relations, and the solutions are obtained in a recursive manner. And that's what the algorithm, there are two algorithms. So basically the prediction requires solving a system of linear equations, which is not so easy when n is large. So the linearity gives a lot of advantage. So there are some algorithms in literature which make this job easy, and these are called, oh sorry, one I is missing. Durbin-Levinson algorithm and innovations algorithm. This is not Durbin, Durbin, BIN. So we are not discussing them. Actually, if you are interested, one may refer to Prockel and Davis or Shumway and Stauffer. So these earlier days, before the computer, nowadays computer will do that. I mean, even if it's 1,000 by 1,000 matrix, computer will simply find it in no time. But earlier days, what happened that people have to find it manually. So inverting 1,000 by 1,000 matrix is not a simple job. So they uses these algorithms to do that. So these algorithms are the two algorithms, Durbin-Levinson algorithm and innovation algorithm. You can also talk in terms of prediction intervals, because when you make the prediction, you can see that it's very easy, because prediction interval is generally considered as the predictor plus or minus the normal alpha cutoff value multiplied by the square root of the variance of the prediction error. ENL stands for the prediction error, so this is the prediction error, and you need to compute this quantity. So that's why computing the forecast error and the corresponding variance of that. So if you're talking about an ARIMA as MA infinity, so what you can see that the prediction error is in terms of these coefficients. So for example, suppose we write MA infinity, where then ENL is N plus L plus this ij is N plus L minus j, and then the variance of this is nothing but 1 plus I1 square plus etc. psi L minus 1 square multiplied by sigma square. So you will be able to get this square root of the variance of the prediction error. Well, this cannot be done in a classroom exercise because this has to be computed for the data. So you definitely require softwares to do that, the prediction error. Okay, that's all about today of the forecasting. So we'll just conclude this. So in a stationary series, the best forecast is given by a conditional expectation. Now that computation is really involved if you don't have a model. But once we have a linear structure like AR, MA, ARMA, it is very easy to carry out this because you really don't actually compute that gamma n. Directly recursive relations can be used so that you can start computing them in a recursive manner. Okay. And another important aspect is that it is not necessary that you have to forecast something at the, something beyond the last observation. You can also make a forecast of something in between observation. So this is also useful for a kind of imputation of the time series. But of course, there is a restriction that we are doing it by a linear predictor, best linear predictor. Okay. And another aspect is that we can also get the confidence interval or the prediction interval corresponding to that once you have the square root of the variance of the error in prediction, forecast error. Okay, thank you.